Thank you, Frank. I'm sorry we don't have time for Q&A. Does anyone in the room has any update about our third speaker, Abdullahi Berth, because we have not heard from him? Okay, if you have, just give me a sign there. So our next speaker is Peter Lewin, is the director of CPU ecosystem at Imagination, and within RISC-V International is the chairman of the Automotive Special Interest Group. Thank you.
Hi, good afternoon, everyone. Can you all hear me okay? Yes. Cool, excellent. Okay, so my short talk this afternoon is around developing an automotive safety island based on RISC-V. And just really follows on nicely from the previous talk. If we have a look at the background to the trends in the automotive industry, we've seen these we know the market trends are electrification, advanced driver assistance and autonomy, and then also connectivity both within the vehicle and from the vehicle to the outside world. These kind of top headline industry trends lead down to a number of different technical demands on the electronics in a system. So there's a demand for largely increased compute requirements, a lot more compute than is traditional. But even more so, there's huge amounts of extra software requirement over previous generations. So more hardware and more software. But all of this comes without easing off on the safety requirements. Safety remains absolutely paramount for everything that goes into automotive. And as well as safety, you've also got security becoming absolutely critical. All of this great enhanced connectivity gives a huge range of new attack vectors. If you can automatically update the software on your car that's going to be in control of your steering, then you really want to make sure that that's being done securely and can't be done by bad actors. To try and make all of this feasibly possible, there's been a drive to consolidate those compute resources. So if we look at the trend of vehicle architectures over the recent decades, so a while ago you'd have discrete ECUs, just kind of an organic architecture that developed where you put an ECU in to do every particular function. You'd have lots of small microcontrollers, maybe just doing one thing. Over the last 10, 15 years, there's been a big drive to consolidate a lot of that functionality into what we're calling domain controllers. So you have a domain controller that's doing all of your bodywork control rather than 20 different MCUs for doing that, all consolidated down onto one. But with domain controllers, you've largely grouped that functionality by the type of function it is. So you have a body controller, a safety controller, an entertainment controller. One of the problems with that is it means that the sensors and the actuators that all of these ECUs have to talk to are distributed physically around the car in lots of different places. So you end up with a lot of wiring. And I was just told yesterday that actually the wiring loom in a modern car can be the heaviest component out of everything. So those kilometers and kilometers of wire, as well as being difficult to fit, difficult to maintain, and a source of reliability problems, is also very heavy with electric vehicles, becomes increasingly important. So there's a move to go from that to zonal controllers, as shown in the diagram here, or more centralized compute as well. So with a zonal controller, we say, well, we're going to put a controller in each corner of the car, and maybe this one's down the center as well. But you're putting those controllers and grouping the functionality based on where the sensors and actuators are. So there's a lot less connectivity, but you're now grouping that functionality differently. And then there's a choice as to how much compute you actually put into the zonal controllers and how much you put into a central compute. That's the direction things are going, but it has a little bit of an interesting feature in terms of safety when you start thinking about those zonal controllers. So just a few facts about functional safety in automotive. If you look at the ISO 26262 standard, it rates every bit of functionality as one of 4 safety integrity levels, through from ASIL A, which is the lowest safety integrity levels, through to ASIL D for those where safety is absolutely critical, things like anti-lock braking. Trying to design anything to ASIL D, however, does incur substantial costs. So as we saw in the last presentation, it's not just about the technical features, it's about how you do that design, the design processes that you need. That can make the actual design process more expensive. It puts a lot of extra requirements in for documentation, so that why this thing is designed as it is can be traced back to the initial requirements. On the technical level, hardware features typically have to include some sort of redundancy measures in order to get the failure rates to an appropriate level. And in many cases, you'll decide just to exclude the use of certain technologies because they're too difficult to analyze or too difficult to prove they're safe, so you'll go without them. Another thing that can cause problems is sharing resources. So if you have a particular piece of memory you share between lots of different applications, well, that then introduces dependencies between those applications and can make that more difficult to analyze. On the right here, I've just got a couple of the typical hardware features we see used in systems that are targeted for ASIL D. Now, the standards don't say you have to use these particular methods. They talk about what the failure rates are, but these are typically what we see. So processors will often use dual-core lockstep. This is where you have an entire separate instantiation of the processor running off the same inputs, so exactly doing the same thing as the first instantiation, just so you can compare the outputs and say, are the two copies doing the same thing? Doesn't build you any more performance, but it costs you the area of an extra processor and that consumes the power of an extra processor. It is a really good way of getting good coverage. If any of the functional logic in the CPU creates an error, you're going to find out about that fairly soon, or at least as soon as it's about to affect the rest of the system. But it's expensive, and it doesn't give you any error correction. If the two outputs don't match, you know something went wrong, but you don't know which was the correct one. If we look at protecting data, there are some other options. You can particularly consider ECC, so putting error correction codes on data, either when it's stored in memory or in transit on buses, can give you detection of when there's an error, can also give you some corrections, so you might be able to recover and continue. And it does that without doubling the size of the memory, as it would if you just used duplication, as we did with lockstep. But it still introduces extra routing. It introduces extra memory, so there's a memory overhead if you put it on memory. A lot of the detection logic may well be on critical paths to your memory, so it may limit the maximum frequency, so there's still a cost with it. So you don't want to design stuff to ASIL D if it doesn't need to be designed to ASIL D. So if we come back to this idea that zonal controllers are now mixing functionality based on where the sensors happen to be located, because we're mixing different types of functionality, it's likely that an ECU will have some ASIL D rated applications that need to be very high safety, and then a number of applications that don't need to be anywhere near ASIL D. So for example, if we have a zonal controller in the rear corner of a car, it may well be running the anti-lock brake functionality. That's ASIL D. That really has to work and has to be safe. But it's also controlling the brake light on that side of the car. You want that to work, but it's not quite the same safety criticality, and it might be ASIL B. So if we've got one ECU with one SoC driving it, but a mix of functions that have different criticality, how are we going to handle that? Well, the most straightforward way would just be treat everything as ASIL D. But as we've seen, although that works, it makes everything very expensive, and particularly if you've got some very high compute requirements and things like that, it would be difficult to do. An alternative is to have two different SoCs in that same electronic control unit, have one doing all of the ASIL D functionality and one doing the less safety critical functionality, which is fine, but again, it adds cost. It's an extra bill of materials. There's communication that could be on chip going across the PCB instead, which can reduce reliability. So what we'd like to do on the right-hand side is mix this criticality of functionality on a single SoC. And we can do that, and this is what the safety island concept is attempting to do, but we have to make sure that that highly critical functionality is isolated and is free from interference from the rest of the SoC. So a simplified diagram of a safety island here, we're saying this is an SoC. In the right-hand side, we've got our general ASIL-B functionality on a compute subsystem with applications processors, graphics processors, maybe some accelerators and DSP. We've got a high-performance interconnect, lots of high-performance memory and peripherals, so a complete compute subsystem on the right-hand side. Then on the left-hand side, we've got a separate compute system, which is much more focused around safety. So this is an ideal application for a real-time RISC-V CPU. In this case, we're showing a lockstep one with some TCMs protected by ECC, as we talked about. This is an entire compute subsystem in its own right, so it's got its own interconnect, memory, and peripherals. But the interconnect on this side isn't focused so much on the optimal performance or absolute highest performance. It's focused on being deterministic and making sure that you know how quickly data is going to be returned in the worst case. Okay. So we've got these two sections of an SoC. They're physically separated. We need power and clock isolation between them so that we don't get a common mode failure if something goes wrong with the clock, for example. And then we also need to ensure, in this case, that nothing that happens on that ASIL-B, on the rest of the SoC, whatever happens there, it can't affect the functionality of the safety island. Because otherwise we've got functionality that we haven't rated, we haven't carefully analyzed, affecting our carefully analyzed safety functionality. Okay. And in fact, if we look at what we mean by freedom from interference, sorry there, Andy. ISO 26262 kind of breaks down this freedom of interference into three categories. It's got timing and execution. So if you've got you've got a task running on the rest of the SoC that's producing some data the safety island is going to use, you might be waiting for that to complete. You've got to make sure the software in the safety island can't just be waiting for that to complete forever if it doesn't complete. We have to assume the rest of the SOC might not be working correctly and make sure that we still make progress and still complete correctly on the ASIL-D side. Memory is another way we can interfere. So if we have some shared memory, again, if the rest of the SoC, that ASIL-B software corrupts the memory that the ASIL-D side is trying to use, then all sorts of nasty things might happen. So typically you'll keep them separate, but actually you want those two worlds to be able to communicate, so you probably will have some shared memory. If you have that shared memory, you've got to make sure that it's very constrained and controlled so that in the safety side, you can analyze what would happen if that data was corrupted. You might say that most of the safety island memory has no access from the rest of the SoC to help that. But if you do want shared buffers, and you do want that configurable, then that has to be configured by the safety critical software so that you can rely on that being configured correctly. And then the third mode is exchange of information. So again, if you've got information being produced by the ASIL-B section, being consumed by the ASIL-D, the ASIL-D code has to make sure it does not trust that data. Any of that data may be corrupted, may be incorrect, so it needs to maybe validate the integrity of it, or at least think, well, what happens if this data coming over isn't correct, doesn't make sense? Make sure that you can still operate correctly. So, coming to think about this safety island, what are its characteristics? Well, it's physically isolated, as we said, so that we make sure a clock glitch or something happening that affects the clock on the rest of the SoC can't affect the safety island. You generally want to keep it as simple as possible because of the costs of doing this to ASIL-D, the costs of analyzing it, the costs of adding that extra performance. So keep it simple, there's less components, it's easier to analyze, easier to design, you reduce that cost overhead, and then also gives you less opportunity for failures. And then what are you going to run on that safety island? Well, it can be, as we've talked about already, some of the general ASIL-D rated functionality, so maybe your anti-lock brake algorithm's going to run on there. It can also do things like act as a monitor and control for the rest of the SoC. So the rest of the SoC still needs some safety. It's still ASIL-B rated in this case. So the safety island can be running in-service BIST on the rest of the SoC to notice when there's errors. It can be monitoring maybe whether anything suspicious is happening that looks like it may be a security flaw. It can control the clocks and the resets, so maybe reset the rest of the system if there's a problem. It's also good for running a lot of the key communication with the rest of the vehicle on that safety island. So if anything goes wrong with the rest of the SoC, at least the SoC is still then communicating and giving that status information to the rest of the vehicle. So the central compute, for example, can know that one of the zonal controllers is not functioning correctly for all of the less safety critical operations. Okay. So in summary, industry trends are driving the move to more compute and much, much more software. This moves the architectures from being separate ECUs through to domain controllers, through to zonal or centralized controllers. This move, therefore, increases the need to mix safety criticality on a single SoC, and a good way of helping to achieve that is to implement a high safety island, which is physically isolated and is physically a whole separate compute subsystem. With that, thank you.